Just 1 second.
Zachary S. Brown, that's me. Deep-learning-NLP-pi data. I can bring this back up if anybody else needs me to. I'll let folks take a couple pictures. All right, cool. I'll switch over to my slides. There we go. All right, so the title of this tutorial is Deep Learning and Modern Natural Language Processing. My name is Zachary Brown. I'm a lead data scientist at S&P Global Market Intelligence. We're a subdivision of S&P Global, that's Standard & Poor's. They do the indices and all of that fun stuff. I do not work for that division. I work for another division that has a pretty sweet web product for doing research into financials and energy sectors and mining and all sorts of different types of things. So our data at Market Intelligence has traditionally been sourced by having a bunch of documents scraped from different places and then having analysts go in and hand extract data and hand annotate data sets. So one of the benefits of that is that we have tons of really, really awesome, very granularly annotated data sets that go back maybe 15, 20 years. And then the other thing that's awesome about being a data scientist there is that we have lots and lots of opportunity to help to automate some of those extraction pieces. And from my personal standpoint, it's really awesome because a lot of that data is just semi-structured or unstructured text. So we get to play around with lots and lots of text. We don't always use deep learning. In fact, I think a lot of the models that we have in production right now don't require deep learning. They're just simple classification models where traditional vectorization methods work pretty well. But we're starting to use it more and more, and I've been trying to learn about it. And yeah, so I developed this talk on it. So an outline of what we're going to talk about. I'm just going to start out by introducing what a general natural language processing problem structure looks like. And then I'll talk about text classification problems, and I'll introduce the perceptron. Now, who knows what I mean when I say perceptron? Hands up. Who has trained a perceptron before? All right. Who has played around with PyTorch before? A few people? All right, cool. So I'm going to go into the kind of painstaking details of how you actually train a deep learning model once for the perceptron. After that, I'm not going to talk about it anymore, and my intention with this talk is not to get down into the optimization nitty-gritty details or not worry too much about the math, but really try to focus on how can we leverage this thing that is deep learning, this architectural approach to solving machine learning problems. And how can I just match that up with NLP problems that have different shapes? Because depending on your task, your NLP problems will have very, very different shapes. So after we talk about text classification and specifically the perceptron, then I'll talk about vectorization and classification with recurrent neural networks. And then we'll go on to talk about sequential models, both from a part of speech tagging example and a more advanced sequence-to-sequence model. So before I get started, does anybody have any questions? No?
What's the name of the repo?
It is deep-learning-NLP-pi data. My name is Zachary S. Brown. That's the GitHub repo name.
Is your presentation out there?
Yeah. So all of this stuff, this is actually in the Jupyter Notebook. I'm using a framework called Rise that just displays your cells as slides. Okay. So this is all of the stuff that I'm going to go through is in the repo. Cool, so on to NLP problem structure. And I apologize to folks that work in NLP because this may come off as a gross oversimplification of problems in that natural language processing space. But from a really, really general standpoint, you might say that you can start out with some sort of a document and you want to perform some task on this document. And in traditional machine learning, you would walk through this long-winded thing of feature engineering. And there are a lot of ways to engineer features from text. There are a lot of traditional ways. There are a lot of like very, very straightforward ways, just counting up the number of words. But there's some sort of a vectorization step where we produce a numerical representation of our text or parts of our text. And then we have some task after we run that vectorization step where we optimize some machine learning algorithm and then produce a model. And then the output of that model when we run inference could be another vector, it could be a vector of probabilities, it could just be a single element. So something like binary document classification, we would run a document through our vectorization process that would produce an input feature vector, and then our task would output just a single number, so just a single a scalar quantity here, and that might be the probability that this thing is true or false. For multi-class document classification, everything up until that last step looks exactly the same. So you vectorize your stuff, you run it through your task, but in this case, you're going to maybe produce 3 different numbers. Maybe this is a softmax distribution over different class probabilities. If we start to get a little bit crazier, let's say that we have a sentence from within an individual document. We might vectorize that thing and produce a vector for every token in the sentence, every word in the sentence. And then we run that through a task, and we produce a vector of maybe a class probability for each one of the words in that sentence. So these are all different shapes of machine learning problems, and we're going to talk about how we can tackle these different types of problem shapes, which correspond to a whole bunch of different problem types that you would have heard about, like named entity recognition, part of speech tagging, sentiment analysis, all of those different things. We're going to talk about how they map onto these just general shapes for data science. So we're going to start out easy with a neural net. So we're going to dip our toe in the water with deep learning and just use a perceptron binary classifier. So it's really, really straightforward. Not a lot of magic going on there, and then we're just going to use a traditional vectorization approach. So if I say TF-IDF, who understands what I mean when I say TF-IDF? All right, so I'll explain a little bit about TF-IDF as well, but that's what we're going to use is a TF-IDF vectorizer, and this is just it's basically just counting up the words in a document and using your word counts as features. All right, so here is our example of text classification and the perceptron. And before I get into that, I'm actually going to take this hoodie off, so if you'll bear with me for a second. Does anybody have any questions before we jump into that?
Just a quick one. So if we're on your GitHub repo,
Oh, yeah.
I'm not sure where to find the notebook that has these slides in it.
That is in the notebooks folder.
Okay.
There's one called 1_perceptron.
Oh, okay.
That's this specific set. So it looks like this when you're just looking at the notebook.
All right.
And then it expands it to cells when you run a RISE server.
Okay.
When you said you had annotated data at S&P,
Uh-huh.
can you give us like an idea of what scale that's on, like how many rows of annotated data you actually have?
So we have. I recently worked on a table modeling problem where we want to identify what table types a particular table is in text, and we already do this pretty well. We extract the data from these tables pretty well, but we need to be able to identify what the table type is to be able to extract it. So for that, I think that I trained. Actually, Paul. This is Paul Arsenovic over here. He actually trained this table classification model. Weren't we using like a million rows or something like that? Yeah.
Several million.
Yeah, and that's just those are individual tables from documents. So it depends on what scale you're talking about. If you're talking about like actual like daily stock data or something, we have tons of that. If you're there's just lots and lots of different data types that we have. Cool. So let's dive in. Oops, I jumped out of my presentation too quickly. So first we'll talk about the perceptron and neural network optimization, and then we'll jump into the example. So this is a perceptron. We have these inputs represented by x1, x2 through xn. These are just your vector inputs for your model. And then we have these lines going to this node right here, and I'll get into that in a second. But these lines represent weights in your model. So in this case, we would have one line, or one weight for every input that we have in this model, and then we might have another weight that represents bias. And this model is really, really similar to something like logistic regression. It produces the same thing. So we have these weights, and then we have this node right here, which just sums up whatever's coming in through this line, and then applies some sort of a nonlinear function called an activation function to that. So here I just have it represented by a simple sigmoid, and then that outputs our y-hat, our prediction for the model. So what does optimization for this thing actually look like? Well, the first thing that we do is we take each one of our inputs, multiply them by the stored weights in that line, and then we sum all of them up, and we might have another line coming in here that's just a bias as well, another parameter that we're learning, and we apply our nonlinearity, and then that gives us our prediction. So we do, that's called a forward pass, where we just take our data, take all the current values of our model, and just run our data forward. It's tons of matrix multiplication once you get more complex neural nets. Then we calculate loss, which is we just define some sort of a loss function that produces a scalar value for each example that you have, and you input your prediction and input your the true value, and this I should say is for supervised learning, so we do have a true value. And then you calculate your gradients, and this is where a little bit of calculus comes in, so I'm not going to go into the nitty-gritty of that, but basically you calculate the contribution of each one of the weights in your model to that loss that you saw. So the loss represents how wrong the model was on that forward pass, on that particular data, particular data element. And then this is figuring out, well, how much did each one of these weights contribute to that thing being wrong? And then what we do is we update those weights. So this is we use different algorithms. Stochastic gradient descent is the biggie that got lots of things started. And we just have some parameter called the learning rate, and we just subtract off from the current value of the weight whatever this contribution of that weight to the loss was. So you just do this a whole bunch of times, go forward through your network, calculate your loss, and then you do what's called back propagation. So you propagate that loss backwards through to your parameters, and then you update your weights. And this seems like a lot of stuff here, but the reason that I'm showing this is because each one of these steps right here is an actual line in PyTorch code. And that's one of the reasons why I was thinking of maybe doing this tutorial in Keras, and Keras is really, really straightforward, and that's where I do a lot of my prototyping. Like if I just want to see if something is a good fit for a deep learning model, I'll pull out Keras. But PyTorch I like because it's very explicit about everything, and it tends to be very cutting edge and get lots of research papers with existing code bases up on GitHub really quickly, so it's nice. Sorry, go ahead.
Quick question. With PyTorch, do you find it more useful for image and text data, or can it be applied for just any machine learning data set?
I mean,
Like the generic human resource data set?
Yeah, you could apply it to, you could use neural networks for any sort of data set that you want. I was actually having a conversation earlier as to why would you use a neural net if you can just use something else that works well? And I would say you don't need to use a neural net if you use something else that works well. Neural nets work really, really well when you can purpose build an architecture for the problem that you're trying to solve. So for images, you can build these convolutional neural nets that, yeah. And I'm going to go into detail about NLP here. Any more questions? Yep.
Why are you using PyTorch and not TensorFlow or any other framework?
Pardon?
Why are you using PyTorch instead of TensorFlow or any other framework?
Because I like, so for the two reasons that I just mentioned a minute ago, I like how explicit it is about everything. If you miss something, PyTorch just won't run, so you really have to understand what's going on, and I like having that level, I like having to have that level of understanding to actually execute things, like the fact that you actually have to define an optimizer and call that optimizer and backprop yourself, like all of those things just appeal to me from the standpoint of really having like a bare bones understanding of what's going on. And like I said, you tend to see a lot of, I mean, not to say that you don't see papers, academic publication code bases in TensorFlow or in Keras or any of these other other code bases as well, but I've noticed there are a lot of them in Torch. So if we want to try out some cutting edge thing and I don't want to code something up from scratch, PyTorch, there's almost always like a PyTorch repository that has a GitHub repository that has it implemented in PyTorch. All right, now we'll move on to a perceptron example. So I'll drop down to the notebook, and can you all see that okay? Should I make the text a little bit bigger? Is that okay? Can I get a thumbs up from the back? Those hard of sight? All right, cool. So the first thing that we're going to do is load in and clean a data set. So we're using this Stanford large movie review data set. So it is literally just a oops, need my imports. So this will take a second to clean it up. So it's just movie reviews and then sentiment. So was this a positive movie review or a negative movie review? This data set's nice because they chose extremely polarized examples. So something that's negative tends to have lots of words in it that have negative connotations, and stuff that's positive tends to have lots of positive connotated words in it. So all I'm doing here is just cleaning up the text a little bit. So I'm using a list comprehension to convert it to lowercase and then get rid of all my punctuation characters. So this isn't super pretty. There's much better frameworks for doing this, but this just gets the job done. And this is just minimal pre-processing. So this is the original. You can see it has a comma in it in a whole bunch in different cases. This is my cleaned text. And now I'm going to use just a traditional vectorization approach, use a TF-IDF vectorizer from scikit-learn to count all the words in this data and then create a vector out of that. So the vector for a new sentence that I pass in is just the count of every word that particular sentence has in it. And well, that's actually a count vectorizer. What a TF-IDF vectorizer does is it takes your term frequency, which is your count, and then it divides by your inverse document frequency. So how many ever documents a particular word occurs in, it just divides by that number. So it has some sense of your overall corpus from that inverse document frequency, but for the most part, you're just doing word counting. So here I just call tfidf.fit text cleaned. So I take my cleaned text, and then I'm going to print out the total tokens in this input corpus, just so we can see with this. Let's see how big data is. So data.shape. So this is 50,000 examples. So with 50,000 movie reviews, how big is this corpus going to be? I'm going to limit it to 1,000 features. So TF-IDF vectorizer has this thing called max features. I'm going to limit it to 1,000, so I don't have to have a super huge neural net here. And then just fit and transform, and then I'm going to just do a little bit of transformation on my labels as well, and then create a training and test set. So this will take just a second. I tried running this on the full corpus. That it'll spit out the size here in just a second, and my computer didn't like me. So yeah, there's 180,000 distinct tokens in that. And you can do things like removing stop words, remove and to reduce that a bit, but you would have naively a vector of length 180,000 to feed into your model. That might work well for some machine learning models, and in fact, some of the machine learning models that we have in production just use TF-IDF vectorization, feed them into an SVM, and they work really well, but we're not going to do that for this particular use case. So now we're going to dive into actually doing our perceptron classifier. So here we have our features of 0. This is just a vector of 1 by 1,000. So, and then our labels of 0 is just a single number. And I have it wrapped in an array here just to make life a little bit easier. So now we're going to use those things, and to make a perceptron, we're going to use something called a linear layer, which is just like the fundamental unit for neural networks. It just takes inputs and multiplies them by some weights, and then gives you some outputs. And this is really just, you can think of it as just a matrix of weights that you're learning. In our case, our matrix, because our input dimension is 1,000 in this case, and our output dimension is 1, it's going to be a matrix of shape 1,000 by 1, so that's just a vector. So we're just learning a vector of weights. I'm also setting bias equal to true here to tell it to learn an extra bias weight. Then we want to squash that down. So I'm just going to define an instance of the sigmoid function here. And all of these things are imported from torch.nn, if anybody's following along at home. And then I'm going to specify a loss function here. And we're going to use binary cross-entropy loss. And that's a typical loss function for binary classification problems. And then we're just going to use basic stochastic gradient descent to optimize this. And when I initialize my optimizer here, I have to pass in the parameters that I actually want to initialize. And the only parameters, our sigmoid doesn't have any parameters. Our loss function doesn't have any parameters. So the only thing that I'm going to pass in are the parameters for my linear layer. And I'll just specify a learning rate of 0.01 because lots of tutorials do that, and I don't want to stand out from the crowd. So that was really anticlimactic, so there's not much fun going on there, but now I have all these objects defined. Now here's where it gets a little bit fun. One of the reasons that I really like PyTorch is that you don't have to have something all wrapped up in a model. You can just create a linear layer, create a vector that will input to that linear layer and just pass it through that, and then look at the output, inspect it. You can do all of this stuff step by step so you really understand what's going on. So we're going to do that. I'm just going to comment out a whole bunch of rows in this notebook, just so everything doesn't print out at once. So here I'm starting by just grabbing an example of the features, an example of the labels, and then I'm converting them to tensors. So I'm converting them both to float tensors. So this is just the fundamental data type, and remember when I said that we have to do a little bit of calculus? Torch knows how to do that calculus with respect to these data types. So that's one of the cool things that it buys you. And then the shape of my feature tensor is just 1 by 1,000. So it's torch.size instead of numpy size or numpy array.size. And cool. Now I'm going to take that and I'm going to pass it through my linear layer. And I do that by calling the .forward method. I think with most modules, .forward is also implemented just as like a call to the actual layer itself. So you can just call linear with parentheses as well, but I like explicitly calling .forward. And then I'll print what the output of that should be. What's the shape of that output? Or do you guys know? What should the shape of my linear layer output be? 1, right? Because we're doing a binary classification problem. So yeah, it's just 1 by 1. So it's just it's a 1 by 1 matrix, which is just a single value. Then we're going to take the sigmoid of that guy and just print out the output of that. So we've squashed whatever value was in there down between 0 and 1. And then we'll calculate the loss. So to calculate the loss, I just take my sigmoid output, and I'm calling .view on this, and all this does is just squash it down to just a single dimension instead of having that additional dimension of 1. And then I feed in whatever my predicted or my actual value is. So now we have our loss, and you see this is kind of interesting. So there's this thing that says grad function, and this tells Torch how to actually calculate that gradient, how to carry out the calculus for this particular thing. For the sigmoid output, you have the gradient function is just sigmoid backwards, so it's the derivative implemented numerically in Torch. So this is the thing that I think is really, really cool. I can propagate this thing backwards by calling loss.backward, and this is going to take that loss and calculate all the gradients of my parameters. So if I propagate that guy backwards, then I can check the weights and biases, and then I can take a step of my optimizer. That's where I actually update the weights, and then I can print out the weights and biases again. This is my bias tensor before. This is my bias gradient, and now my bias tensor has been updated. So this is it's all, there's like no magic here. It's literally just like the only magic is that it really does a good job of keeping track of derivatives. And there's something called AutoGrad in Torch that does that really well. So now on to actually training our neural net. So we have all of these feature vectors. the first thing, I'm just going to loop through all of my examples, and I'm just going to have this thing called iterator, which keeps track of those. I'm going to zero out my gradients at every step because I don't want to just keep accumulating gradients that are added to my weights. Then I'm going to grab a feature and target. I'm going to convert them to float tensors, run them through my linear layer, run them through my sigmoid layer, calculate my loss, add it to total loss so I can keep track of how much actual loss I have here, call backwards, and then take a step. All of these things are really, really common, like boilerplate for any sort of PyTorch model that you see. And that'll run, there's 37,000 training examples in this little toy data set, and boom, all right, it's done. Now, how well did it do? I can take the same data, or the same exact process, and just run my test data through it. There's one thing that you'll see later on where I call like linear.eval, which converts your layers into an evaluation mode, and that just turns off things that are undesirable during inference. But a linear layer in this example doesn't have any of those things, so we don't have to worry about that. We see after training on our data set, we have an accuracy of 0.8. So that's not very great. So why is everybody super excited about deep learning? So two things. This isn't the perfect problem for deep learning. We're not using deep learning to vectorize our data set, and I've only run my data set through my model once. So for traditional machine learning models or typical machine learning models, you usually just train on your data once, or maybe you do some cross-val and then try to estimate the performance of your model on a holdout data set. But you typically just run your data through once. Because we're doing stochastic gradient descent, we can just run our data through multiple times. And you will get to a point where you're not going to get any more gains on there, but you'll see your metrics actually leveling out. So if you've ever looked into any sort of deep learning blogs or anything and seen the term epoch, that's just talking about the number of times that you're running your data through your model. So I actually have a model implemented here, so I can pull that up in just a second. But this is what your actual training would look like. So this model that I have that I'm going to define right here takes in what the max features, what the input shape of my data is, and just gives me this model thing. And now this model has a dot forward method, and that does all the stuff that I was doing. That runs it through the linear layer and executes the sigmoid. I'm going to specify my binary cross entropy, and I'm going to run this for 5 epochs now. So we're doing all the same stuff that I just did, and we'll print out the accuracy for each one of these. And while that's running, I'm not sure, because I'm a slow talker, that we're going to have time for me to pause for people to try, like, plink around on their keyboards and try out the examples that I have. But in this folder, I have a -stub file for each one of these notebooks, and the thing that I just walked through, where I defined each one of the layers and then passed a piece of data through each one of the layers, that spot is blank in all of those notebooks. So I explain how to do it, and then that's for you to actually implement. So I feel like hands on the keyboard is a really, really great way to learn. So I hope that somebody will take advantage of that. All right, so this thing finished. So our loss per epoch is decreasing overall, which is good, and our validation accuracy has gone up, which is good as well. Sorry, go ahead.
Conceptually, can you help me understand why, you said stochastically, for some reason, why can you rerun?
So you're just optimizing the parameters, so you can just keep updating the parameters on your, just keep updating. So I'm feeding it through one example at a time. What you would normally do is I didn't want to get too deep into it, but what you would normally do for, you would normally run mini batch stochastic gradient descent, where you grab a random batch from your data set and then run that through and grab another random batch. And if you just keep running it through, it's just a feature of deep learning that your loss will keep decreasing to some extent. So picture yourself like you have this loss function space, right? And after you run through, you start out at some randomized spot, and then you explore by running through the data set, this loss feature space. Well, now you're here, and when you saw the first example, you were up here before. So now the first example might nudge you a little bit more in the right direction because you're in a different space, in a different part of your loss feature space. Does that make sense? All right, cool.
Also because we have the learning right?
What? Yeah, and you
we
can.
are not learning everything from each object all the time. So
Yes, you are scaling by a learning rate as well, which you can. There's like stochastic gradient descent is the most naive way to optimize this, but there are a bunch of other different optimization algorithms that both modify your learning rate and take into account past steps as well. So there's something called like momentum and ADA grad and Atom. There's a handful of different optimizers. So here, we're going to just look really quickly at a multi-class model, and I'm just going to run through this quickly just to show you the difference between a binary output and a multi-class output. So here we're just using Stack Overflow questions and answers, and I've just pulled out labels, 8 different label types. Run through the same exact stuff that we did before, and now we have a linear layer, but instead of having an output size of 1, we have an output size of our label size, which is 8. So instead of just outputting a single value, the output shape from this linear layer will be of dimension 8, so 1 by 8. And we can walk through that same exercise again. Oh, I have to run this guy. And you'll see that, oh, I'm sorry, it's not 8, it's 5. So you'll see that the shape from your linear output is just a 1 by 5 vector as well. And your softmax output shape is just going to be 1 by 5 as well. So here, the only things that we have to change to take this from a binary classifier to a multi-class classifier are to change the dimension, the output dimension of our linear layer. And we also want to change our loss function. So we want to change our the squishing function that we have here. So we're going to use something called softmax, which is just the multi-dimensional, like a multi-dimensional version of the sigmoid. So we're going to use something called log softmax here, because log softmax works with this negative log likelihood loss function. So these two you'll see commonly together. I wanted to explicitly call out that we're using a softmax on this layer. There's another output loss function criteria that combines these two together called cross entropy loss. So that's just implementing cross entropy there. And then we can do the same thing training this model. And this will take just a minute longer to train than the other one because there's a little bit more data. I think I have 100,000 training examples here. And we can get pretty good accuracy on this. I think it's like around 80 or something like that. So does anybody have any questions before we move on to sequential models? Everything in here totally straightforward? Yeah? If you guys have any questions, ask. Yeah. You can think of a tensor as just being Torch's version of a NumPy array. So like a NumPy, you can have an array of floats in NumPy that's optimized for vectorized processing. That's just Torch's version of that. And it has this additional feature that Torch is aware of how to calculate the gradient of different types of tensors with respect to their inputs and outputs.
What was your Y function again, your prediction function?
What was my prediction
Yeah,
function?
you're trying your when you predict your accuracy score, when you do that against?
So what was the Y, or what was my? So my Y is just the whether or not it was a positive or negative in movie review.
Okay, gotcha.
Yep.
You're changing that right to more of a multi-class.
Yeah, so in the second example, that was, there were 5. So it was Stack Overflow questions and answers. So it was the question and then whether or not the answer was tagged with Python, Java, JavaScript, or a couple different languages. Yeah, so after a few epochs, this looks like it's getting up around 70% overall accuracy on a 5-class data set. So if we're just training this for a couple minutes, that's not horrible. But it's not doing anything really that we couldn't do with just like an SVM or any type of other classifier. So can anybody tell me what the thing that we neglected with our naive vectorization there is? Sorry, go ahead.
Grammar and structure.
Yeah, grammar and structure. So things being next to each other can mean things. With TF-IDF vectorization, you can take some of that into account by using, I just used unigrams there, so just single words. You can take bigrams, trigrams, and that's cool. That will work. If you have a really good feature selection methodology, then that can work really, really well. But that can also explode your feature space. If you count the number of individual words, that's one thing. But then if you start counting pairs of words, then you have a lot more features there.
So this would be good for like language translation?
Yes, and we'll get to that. You're getting ahead of me though. Getting ahead of
I
me.
didn't mean to.
Yeah, it's okay. It's
I'm the
okay.
dumbest one here, actually.
For the perceptron, how do you determine how many big layers that you add?
Yeah, so that's a great question. So I didn't talk about that at all. I just had a single layer in there, but you can have a whole bunch of linear layers just stacked on each other, and those are called hidden layers. You have your input layer, and then you have anything that's between your input and output layer is called a hidden layer, and it's called a hidden layer because it doesn't directly interact with the input or output. And you can have, it's really, you can think of it as just introducing additional parameters into your model. So if you think that your data is like really, really, really complex, and you want to capture a lot of complex dependencies, you could have like 10 layers in there. It's going to take longer to train, and you need to, at that point, balance the number of parameters that you have in your model versus the number of training examples that you have. All right. So we didn't take into account what I would call context of all of the words that we fed into our naive classifier there. So how can we do that? Recursive neural networks provide a way for us to do that. So they look at the context around each thing that you're turning into a vector, and they allow you to incorporate some of that into it. So here we'll talk about using recurrent neural networks for encoding for text classification. We'll talk about just recurrent neural networks in general. We'll touch briefly on word embeddings, and then we'll get into an example. Cool, so multi-class document classification is what we just did. We used TF-IDF vectorization, and then we used a perceptron classifier here. So now we're going to use an RNN, a recursive neural net, to vectorize here, and then we're still going to use a perceptron classifier at the end. We're still just going to use that same architecture of just a linear layer feeding into an n-dimensional output where n is our number of classes. So that thing is going to stay pretty consistent through the rest of this tutorial. So what is a recurrent neural network? Have people seen this diagram before? It's all over the internet. If you go to like any blog, everybody's stealing this from, I think that this is the guy that created these visuals, Christopher Ola. So I'm going to credit him with these pretty visuals that I did not create. But this is a recurrent neural network. It takes some sort of input, and in this case, this xt, this is a vector. And it outputs some output, some h sub t, and that's a vector. The letters here are a little bit strange. So this H stands for hypothesis, but that's just our output vector. So this, in many ways, just looks like a single linear layer, or a single perceptron, where this box right here would be the perceptron. So it takes in an output, it takes in an input of whatever shape that we have, and outputs a vector of a different shape. But then we had this recurrent connection here. So if we unroll what this thing looks like, it allows us to feed in a sequence of things and have it learn, have it bake into the output for a particular time step information about the input from the previous time step. So we can feed in, let's say each one of these vectors represents a word, or let's say each one of these inputs is just a state, like a stock price at a particular day or something. You could feed those in, and then the recurrent neural network, this recurrent node here, outputs what's called the hidden state to the next, to computation of the output for the next time step. So one important thing to note here is that this A is the same across all of here, meaning that you're updating the same set of weights. These aren't a whole bunch of different nodes. This is one node with the same internal weights that are getting updated at every time step. So the nice thing about recurrent neural networks is because there's this right arrow that propagates information forward this way, if we have time or if we have sequential data, this time step, the output at this time step, knows a little bit about the input at this time step. It has context baked in. And this is just a single directional recurrent neural net, so with the arrows just going one way. So it's just baking in information from the previous iterations of whatever sequence that we're looking at. But you can have something called a bidirectional recurrent neural net, which just does this thing both ways and then just like stacks the vectors on top of each other. If you want to bake in contextual information from both sides of whatever your particular output is. So a vanilla recurrent neural network just takes your input and the hidden state from the previous time step, combines them, runs a tan-H activation function traditionally on it, and then outputs your output and outputs your output to the next time step as well. So this works pretty well for short sequences. It doesn't work particularly well as your sequence length gets really, really big. And that's because if you remember back when I said that we're doing a little bit of calculus here, your derivatives and the contribution to your loss from each one of those successive derivatives, they can either get really, really big or really, really small and kind of squash information from really previous time steps. So vanilla recurrent neural networks don't have a very long memory. So they created this thing called a long short-term memory network. And I'm not going to get into the complicated awesomeness that's going on here. But two things to know about these. They retain their memory better. And from a practical point of view, they have two input states here. So you're going to be feeding in two vectors from a previous time step. So this one up at the top is called the hidden state, just like for a vanilla recurrent neural network. This one at the bottom is called a cell state. And these just contain different parts of information that allow you to propagate information for longer. So for a deeper dive into the necessity for and the implementation of LSTMs, check out that blog where I pulled these images from, because he does a really, really good job of doing a deep dive into why it doesn't work that well for vanilla neural nets and why we need to use LSTMs. So because they work better for a lot of slightly longer sequences, and we have slightly longer sequences here, I'm going to be using LSTMs. And that just means that when I refer to something as hidden, it's really in Python just a tuple of vectors, or a tuple of torch tensors. One is our hidden state, and one is our cell state. So that's the biggest reason that I'm calling this out here. Somebody have a question? No?
I have a quick question. So when you pass it, it's actually a Python tuple of PyTorch tensors, or is it a multi-dimensional PyTorch?
It's just, yeah, you can just pass in a Python tuple, and you'll see that in the code when I initialize those guys. So if we want to, before with our TF-IDF vectorizer, we just encoded a whole sequence of words, just text, naively to a single vector. We can do the same thing by using an LSTM if we just ignore all of the hidden state, or all of the outputs, up until the last one, because if this recurrent neural network has worked right, then this should contain contextual information from the entire past. So this is a way of encoding a sequence of things into a single vector, but also having that single vector be context aware of how the things that contributed to it interacted. So like I said, for sequence classification, this guy just outputs a vector. So we can just toss our perceptron on the end of that and do our actual sequence classification. So an example of that might be we feed in words here, and then we output if it's positive or negative. So simple sentiment classification like our first problem was. But what's the problem with this diagram? What haven't we talked about here yet? I said that the inputs to this are vectors, right? And I have words here. So how do we feed a word into something that's expecting a vector? We have to vectorize those somehow, right? So a naive way would just be to use a one-hot encoding strategy, which is what our count vectorizer is essentially doing, right? It's just saying that I have 500,000 words, so the word "the" is 1, and then 499,999 zeros, right? So what about the inputs to the RNN? So I could use, this is cut off a little bit, that's okay. I could use just this naive diagonal representation where I one-hot encode all of our words. That's still a really high-dimensional representation, and I don't want to have to do that. So it would be cool if I could get a dense representation, and it would be even cooler if this dense representation knew a little bit about the word. So have you guys heard of word2vec? Or glove embeddings or word embeddings in general. There are a lot of ways to get dense representations of words using unsupervised machine learning approaches. I'm not going to get into that, but instead, I'm just going to treat each one of these words as just a vector of weights. And that's basically what word2vec and glove and all of the, well, word2vec, all the neural-based approaches are doing. So I'm just going to initialize what I'm going to call an embedding layer with just a set of weights of dimension n for every single one of my words, and I'm going to let the model learn a representation for that word. So the cool thing is, if you train a model on a classification task that's really specific to like a domain-specific corpus, let's say you're working in finance, you can take, if you use one of these embedding layers to learn weights for each one of the words that's going into your model, the embeddings that you've learned are going to be really useful for other tasks as well, especially if it's really domain specific. Everybody likes to play around with glove embeddings and word2vec embeddings and all of those other fun ones because they can give you a little bit of lift on your naive model. But from a practical standpoint, if you're working in a specific domain, if you're working in healthcare or finance or anything like that, and you train your own embeddings, that's going to give you substantial lift over one of these publicly available embeddings or it could give you substantial lift over the publicly available embeddings that were trained on something like Wikipedia. Sorry, go ahead.
Something categorical embeddings for like a supervised learning classification problem?
Categorical embeddings. You mean like a one-hot encoding of categorical variables?
I mean, so you could, I've heard people talk about basically using deep learning for structured data and then creating categorical embeddings of categorical data, which you can then use as features.
Yeah, so you could, I mean, we're essentially treating this, if we were to flip this towards like a categorical lens, we're essentially just treating all of our words as different categories, right? And just learning a vector for each one of those. So if you have like, I don't know, a handful of categories, you could just create an embedding layer for those and learn embeddings for your categories as well, and feed those in as a separate input to your neural net. So I haven't done that, but there's a guy on my team that keeps talking about it, so I feel like there's a chance that I will at some point. Yep. So cool. So we are going to just let our model, we're going to feed in words, and each one of these words is going to have a vector of weights associated with it, and we're just going to let our model learn what those weights are. So let's jump into our LSTM text encoding example. So again, I have all of these fun inputs, or all of these fun imports, and I'm going to do the same exact text cleaning that I did before. And what we're using here is the R8 data set. So this is from Reuters, and this is just an annotated, I think it's from the 80s or something, but it's just a hand annotated data set of topic content, and I think that there's 8 different labels that we have here. So it's a whole bunch of news articles and then a hand annotated label of like this is about earnings and this is about acquisitions or something like that. So we can say data.label.nUnique. Yeah, so this is the use case where we have 8 different output labels. So what am I doing here? Oh yeah, so when we create this embedding layer, what we want to do is figure out how big, so the embedding layer is essentially just a dictionary lookup between a word and a vector of weights for that word. And our PyTorch just uses that and optimizes those weights just like we were doing for other things. But what we need to do to be able to initialize that embedding layer, the embedding layer doesn't like an actual text string as its input. So first you have to integer encode all of your words. So you have to figure out how many words you have and integer encode all of your words. And then the embedding layer will just expect a sequence of integers or just a single integer. And it will convert that into a vector for you. So all I'm doing here is just splitting the text up, figuring out how many words I have for it, and then calling that my vocab size, figuring out how many labels I have for it and calling that my label size. And then I'm creating two different dictionaries here. And there are, just to be clear, there are a lot of, this is like kind of hacky code, I would say. This is just stuff that I put together to illustrate the point and show you how you would do it by hand. Torch actually has a lot of utility and convenience functions that will do all of this stuff for you, but it's just like one call on an entire text data set, and I wanted to explicitly show what that's doing under the hood. So we create a dictionary that's word to index. So that just translates a word to an integer encoded index, and then index to word so we can get back. Same thing for labels. And then we have a text encoded and a label encoded column to our data frame, pulling the values out of the label encoded and pulling the features out of the text encoded. So after I do that, that should run quickly. Our labels are just single integers for a single training example. And I can do like labels :10s. You can see it's just a whole lot of individual labels. And then features of 0. These are the integer encoding of the actual words in that sentence. So I just split them up on white space, encoded each one as an integer, and then this is what we're going to feed into our embedding layer. So it's going to take this integer, 19,253, and instead of having to have a vector of length 19,000, I can say, well, I want to represent this word in a vector of length 100 of floating point numbers. Then I have 100 floating point numbers instead of this one-hot encoded grossness. So now let's start putting the pieces of the actual model together. So this is our embedding layer. You just have to specify the number of embeddings so it knows how much memory to allocate and your embedding dimension. So I want to take each one of those words and have a representation of that word of dimension 100. Glove and Word2Vec, I think, have open data sets that are of dimension like 100 and 300 and maybe even 50 as well. So 100's a nice round number. Then I'm going to take an LSTM layer. So this is that long short-term memory. And all we have to do is specify the input size. That's the length of our input vector that's coming up from the bottom. And that should be the same as our hidden dimension because I've encoded the words as these 100-dimensional vectors, and then I'm going to pass that up into my LSTM. And then I can separately specify the hidden size, and that's going to be the length of this vector that's being passed over to the right. So any questions on that? And that's also, I'm sorry, going to be the length of the output size vector as well. So I create an LSTM layer, and then this is where you were asking if it's just a Python tuple. So I'm going to initialize my hidden layer and my context vector, or my hidden vector and my context vector to just zeros. So I do that, it's just like numpy.zeros, just torch.zeros, and I want it to be of shape 1, 1, 50. This is this middle dimension right here is my batch size, and for all of the stuff that I'm doing here, I'm not doing any batching of my data. Usually, to run Torch in best practice and to be memory efficient and have things actually run quickly, you want to batch your data, so send through 50 examples at once. For the sake of this tutorial, I'm not doing that because then you have to worry about making sure that all your sequences are the same length, and you have to do things like padding, and that just goes down a gross rabbit hole. There's, again, convenience functions to handle all of that, but I would feel like I would be doing you guys a disservice to just use convenience functions all over the place. So here I initialize my hidden state and my context, or my cell state to zeros. And then just call that tuple lstm.hidden. So that's my hidden state. And then for my perceptron, I have this linear layer that's going to take the output dimension from my LSTM. So this thing up here is going to be a 1 by 50 vector. And reshape that into my label size. So this is just a matrix that's going to do matrix multiplication on that vector and output something of the dimension of my label size. And then I'm going to, again, use my log softmax and my negative log likelihood loss on this. My log softmax, I actually have to specify a dimension here. So I'm specifying dimension equals 1, so it calculates along the right dimension. And then we're good to go. So here, again, we'll walk through each one of those steps, just sending a single example through to make sure that we know what we know what's going on here. So, and I'm not going to walk through the optimization part here, but my integer feature sequence shape is 62. And then my integer target shape is 1. So this means that I have a one-dimensional vector for my output. That's just the label, the integer encoding of the label. And then for my input sequence, I have a sequence that's 62 words long for this first example. So now I'm going to pass that through the embedding layer. And what should the shape of this be? I pass a sequence of 62 through my embedding layer. We all get to drink beer really soon, I promise. There's beer upstairs. So my embedding layer is of dimension 100. So I'm going to pass each one of these integers through, and it's just going to convert that into a sequence of 100 dimensional vectors. So it's going to be 62 by 100 instead of just 62 now. So now I have a vector of, or a sequence of 100 dimensional vectors. And now I can feed that sequence into my LSTM. And that's going to produce two different outputs. So or actually one thing, I need to call, because LSTMs so all the other layers have an option to not work in batch mode. LSTMs require that you have this additional batch dimension. So I'm going to call this .unsqueeze method on the first dimension to basically just like, if I have a two-dimensional vector, I'm just going to add another dimension in the middle. So the shape of this guy is going to be whatever the shape of this guy was, whatever the first dimension of this, then 1, and then the second dimension of this. So I'm just adding an additional batch dimension in there. And then we will pass that guy through the LSTM. So now we have our LSTM output is a vector of 62 by our batch size by 50. So for every single input that we had in that sequence, you remember in our unrolled LSTM diagram, we had an output at the top for every single one of those. For sequence classification, we don't need to use all of those outputs. We could take those and try to come up with some fancy way of like maybe smushing them down into a single vector and then feeding those into our perceptron. But that last output state should have most of that contextual information encoded in it. So we'll just take the last output state. So here, we're going to retain only the final output state, and this should just be a 1 by 50 vector. So now we can feed that into our perceptron. We've encoded that entire sequence into a vector of size 50. And now we can just feed that into a normal linear layer and output with an output dimension of whatever our class size, number of classes is, and that should work. I hope that it'll work. So we run that through our final linear layer, and then we run it through our softmax, and then we can calculate our loss. So I'll run all of these guys together. So we have a loss value of 1.88, and that doesn't mean anything to me right now because we haven't let this train, so I don't know what that's in relation to. But we see that our linear output outputs a 1 by 8. Our softmax output, again, outputs a 1 by 8 because that's just applying a function element-wise to that. And then our target shape is just a single integer. So when we input our loss, when we input to our loss, this should be a sequence of integers, and then this should be a sequence. This should have one element for every single class that you have because it's the probability for each one of those classes. So again, I just wrapped all of that stuff up into a module, and if anybody wants me to dive into what the actual model, the boilerplate and everything for the model looks like, I'm happy to do that maybe right after I run through this section so we can get a peek at that. But I defined an RNN classifier model, which just executes all of those steps in a method called forward. So all it's doing is on init, it's defining all of those things that I did in that first cell, which is your linear layer, your LSTM layer, your embedding layer, and then calling all of those things in the same sequence that I just did on forward. So I'm specifying an optimizer and my loss function here. Here I'm going to run it for 10 epochs, calling model.train, although I don't think I need to, looping through all of the data, and then zeroing out my gradient, doing all of those things that we did before. For the sake of time, I'm just going to run this on the first 32 elements of the sequence. A lot of times in practice will do this just to make sure that my model is actually running, because otherwise it's kind of a pain in the butt if you're feeding in these long sequences and then something blows up on the second epoch or something. It's kind of a pain in the butt. So we'll run this guy, and while this is running, I can actually open up to see what this RNN classifier model looks like. If anybody's interested. Is anybody interested, or I can keep Sublime Text closed? Yeah? All right. I got one nod, so that's enough for me. Modules, Sublime, application. All right, so I have all my same inputs here, and then with any sort of PyTorch model, all of this stuff is just like your basic boilerplate. So you'll have an init method, which calls the initialization of its super class, and then you just define, all of this is just boilerplate, the super init. But this specifies your model parameters. So in this case, I had a hidden dim size, an embedding dim size, vocab size, all of this stuff. And then I just initialize all of those different layer types that I have. So I have my embedding layer, my LSTM, my linear, specify my batch size, and then I have my log softmax, and then I have this thing called init hidden, which just does that. It just creates the first element of my hidden state and my cell state. And then your forward pass. So this is just running in a particular value of your input through all of those layers. So your initializer and your forward pass are the two things that are required for all of your PyTorch models. So the first time one of the guys on my team recommended that I check out PyTorch, I looked at the tutorial and saw that I had to do all of this to do pretty much anything, and then I promptly closed that notebook and imported Kira's in another one. So it seems like a lot of overhead, but once you just get used to once you write this out a couple times, it's just oh yeah, then you either just automatically type it out from muscle memory, or you just copy and paste from some other notebook that you have. Go ahead.
Have you used the SAI to the wrapper for PyTorch?
I have not yet. I am really excited to, though. I haven't had a use case since the last use case that I had for it. I started developing right before FastAI did their main release of. I think they're on they're on some official release now. And right before they did that, I started developing, and then I wasn't going to just switch code bases. But I'm waiting for another use case to use it. It's supposed to be awesome, and I mean it has a lot of stuff that's really close to really close to the heartbeat of academic research. There's lots of really, really like state-of-the-art models in there. So just for everybody not familiar, FastAI is a company that has a really awesome deep learning package that does a lot of this stuff for you. It has a lot of pre-configured architectures for handling these types of problems, and it's all written in PyTorch under the hood. So there's lots of cool stuff there. So I'll go back to the notebook, and this guy is training. So our loss is at 0.97, and our accuracy is at 0.74. So in the interest of time, we have about 25 more minutes, I think. I'll move on to the next section. Oh yeah, so this is going up. I just wanted to wait so you guys believe me that I'm actually increasing the accuracy as I let this thing train. So do we have any more questions here before I move on to actually doing some sequence-to-sequence type things? No?
Just had a quick one.
Mm-hmm.
That Sublime Text command line, does that come with Sublime Text, or is that something you'll
Yeah, you just have to create a symlink, and I don't know, every single time I get a new computer, I just Google Sublime Text command line, and there's some tutorial, or there's some blog post from like 2011 or something that just tells you where the default location that it installs that is. But yeah, it's just not on your path by default. Mm-hmm.
Question. You create the word embedding using all the data set or just the training set? I'm not sure.
The word embeddings, I used the entire data set.
Did you? Well, data leaking.
Yeah, that's a good question. So if you don't do that, then so the way to get around that is to introduce an unknown token, and because otherwise you'll go to pass through your test example, and you just won't have that in there, and it'll fail. So you can pass through an unknown token that it just returns if it doesn't have that particular thing in there. But that is a good point. Yeah, you could potentially have some data leakage there if you do that. If you're using embeddings trained from somewhere else, then you don't have to worry about that, right? Cool. Any other questions?
Total maybe with the hidden layers, in your Sublime Text, you showed I think you had 2 hidden layers. Was that right, or you just had?
These guys. So these are the hidden states for the LSTM. So this is the hidden state vector, and this is the cell state vector.
So, what is the autograd?
Oh yeah, sorry. This is So Torch, previous versions of Torch, prior to the 1.0 release, which just happened, I don't know, like a month or two ago. Prior to that, Torch didn't have the ability to automatically know how to differentiate a tensor with respect to its inputs and outputs. So you had to wrap it in this torch.autograd.variable. Autograd is the package that does the automatic differentiation, and it knew how to differentiate variables. So you just saw this everywhere in the code, and it was kind of annoying. And I copied and pasted some code that I had from before the release over here.
How many hidden layers do you
Uh,
in this run, in this thing that you're distributing?
In this network, I have a single linear layer, which you can consider like a hidden layer in the network. So actually, it's probably better if I go back to this diagram. So you can think of this being a hidden layer that has a complex. This has a hidden state, which is a vector, a cell state, which is a vector, and then a whole bunch of weights that are the hidden layer for this LSTM. So this would have a whole bunch of weights that would be hidden layer weights, I guess. And then your perceptron out portion of this would have a whole bunch of hidden layer weights as well.
I think last time I used PyTorch, the LSTM cell
Or one of the recurrent cells had an init on that was like the number of layers and layers. So I think you can actually stack these LSTM cells so that that hidden output coming out the top goes into another LSTM cell, which then has the output going into the side that goes back.
Yeah.
You have two levels of data cycling.
Yeah. Yeah, so you can stack this thing on top of itself and just create a whole bunch of those. That's a really good point. Yeah.
And then in the latest state of the art, if you've heard of Elmo, look up Elmo embeddings. You look at that, right? They have two or three different layers, and they find the different ones that go to different types of information, like semantic and syntactic, depending on how deep you are in the LSD and stuff.
Yeah. So Elmo is a new type of word embedding approach that finds multiple representations that are good for different tasks, all by just training different layers. And the top layer might be representative of like contextual information or semantic information. The bottom layer might be much more like lower level encoding.
Another maybe question. I mean, obviously you're doing this on your laptop, right? It's not, or is it doing it on the cloud somewhere?
No. This is running on my laptop, so I'm not using any GPU acceleration here. If you do that, you're going to have a bad time. You're going to be waiting for a long time. Like I'm using, it took me a while to find these data sets that I have listed here, and some of them I even downsampled. So these are all the data sets that I used for the for this tutorial. I also have a directory in the notebooks directory called like dataset prep or something that shows you how like I got them, and it gives you traceability into how I processed them. And yeah, some of them I had to downsample. Like this, which one? The Stack Overflow Q&A is like billions and billions of rows, so that would be super fun to like pop onto a GPU machine and train a really, really big neural net on. But it's not a good idea to do that on your laptop. It'll take a while, and it'll make I mean, you can probably hear the fan on my laptop, and that's just it's just on a fairly small network.
But is it all set up in your laptop to use the GPUs if needed to?
I don't have a GPU. I don't have an NVIDIA GPU in this guy.
And it only takes NVIDIA, if I thought.
I've looked into
I know this is AMD for the most part, right? Apple nowadays.
Yeah. So Apple, this is a whole different discussion. But yeah. So if I wanted to do this, I would just get an external NVIDIA GPU, because it's just so tightly integrated with the CUDA library, and to try to get that, That's
what I was wondering. I mean, everybody uses Mac, but I mean, so when you actually want to do this, do you jump onto an external for different?
You jump on. I mean, so Amazon has a really awesome deep learning AMI, deep learning image. And you can just, like, if I want to do anything heavy duty, I'll just, it takes like 5 minutes to spin one up on one of Amazon's heavy duty GPU instances. Actually, I would highly recommend, if you want to play around with this stuff.
AWS account for
that? You get an AWS account. It's, I think, 90 cents an hour for a P2 instance, which is pretty beefy to do like a step up from what I'm doing here. And like, I don't know, for what, $5-10, you can play around with it for an entire day and then just tear it down. Like it's totally worth it if you want to get into it. The only thing that I'm not doing here is explicitly sending the data to the GPU. So there's if I were to change my code to make it function on a GPU, there would be a whole bunch of checks to see if a GPU is available, and there's a torch method for that. And then if the GPU is available, you would just call .CUDA on all of your tensors, and that just sends it to the GPU, and then it puts the processing there. You don't want to do that if you're just running in serial like I am, just running single examples through, because then you're just going to be copying and pasting back and forth, just copying back and forth between the GPU all the time. But it really helps out once you start having batches of lots of data. So you send a whole bunch of data over the GPU. It does the calculation really quickly, and then it sends it back. Question back there?
Google might still give a $200 credit to play around with it.
Yeah, and actually, one of the presenters one of the presenters tomorrow that's doing the tutorial, I think his name is Robert Alvarez. He's doing an introduction to PyTorch. I saw him give one previously, and he did it using Google's Colab, and they will let you run things on GPUs for free if you run it in their notebook. And you can actually, when he did his tutorial, they actually had a TPU option there too, which is like, wow. So yeah, if you want to play around with this stuff and not have to spin up an AMI in AWS, that would be a good option as well. Cool, so this thing is making my laptop slow now, but yeah, so it got up to like 90% accuracy. This data set, I looked at like benchmarks on it, and like 98% accuracy is like pretty standard, or pretty like state-of-the-art accuracy on this guy. So this, I'm pretty sure, would eventually get up there if I let it run for a little while. But I'm going to kill this and then move on to the, I swear to God, this stands for part of speech tagging. So the part of speech tagging section of this. So we've, up until now, just been talking about classification. So we have this like sequence of text, we have a document, we have whatever, and we want to be able to just output a single value. But what if we want to output a sequence? There's a whole bunch of different use cases for this. So we do some vectorization, and that produces vectors of our words or something. And then let's say we just wanted to output a single value for each one of those words. What's a good example use case for something like that? Like, what's a real world use case that we might?
Part identification.
Yeah. So part of speech, I guess I gave it away. That's a stupid question. I gave it away with the name of the notebook. But things like named entity recognition, there's a whole bunch of different tasks that you can do here. Sentiment analysis of individual words you could do. There's lots of different things. So part of speech tagging, named entity recognition. You could also do extractive summarization. So think of a summarization model where you feed in a paragraph of text, and you just want to figure out what words you can chop out to produce a good summary of that text. If you have like news articles and headlines, you can play around with modeling that and see if you can just chop out particular words and produce a summary of that. So. And that would just be like a binary output on each one of the words that you have, saying, yes, I want to keep this, or no, I want to throw this away. So there's lots of different use cases for this, and we're going to focus on part of speech tagging.
Could you use that theme?
For what?
Like theming, not just summarization, but like what's this really about in a few words?
Probably. Yeah. So you couldn't use this type of model, but there are models. If you want to look into something like that, look up abstractive summarization. So abstractive summarization is a type of sequence-to-sequence model that it has some similarities to the last type of model that we're going to look at, and that can produce, instead of extractive, where you're just chopping words out, abstractive summarization can output words that weren't actually in the initial document. So if you trained a model that was specifically on like a theme of a particular portion of text, you could probably get something working. That's a really interesting use case, though.
So like Amazon, if you look at those, what's the different types of themes that people are talking about that product or something?
Yeah. That would be interesting. All right, cool. So, any more questions before we hop into sequence model? Yep.
How easy is issue identification in such cases? Like, we have a part on a review, and we say, the part doesn't work, the pipe's leaking, and leaking is the issue there. How easy it is to identify those in your document?
I don't know. I don't know off the top of my head. I would say if you want to identify particular terms in an input sequence that are important to a particular output, does that make sense? So like you know that something's broken.
Essentially negative words or negative issues related to any set of products.
Yeah.
And that's essentially a real life use case we had where the client really wanted to identify all different kinds of issues that could come to any set of products. And some of them have just 3 comments to around 20,000 comments.
All right.
Very fair part.
So there's a lot of non-deep learning approaches that would probably work for that, just like simple like text statistics over like a large body of text. But if you wanted to have a deep learning model, you could use something like we're going to talk about, like a similar to a part of speech tagger, except just have your output for each token in your sequence just be yes or no, this was problematic. The issue with that is you would have to have an annotated data set that has for every single word in this review, this was problematic, this wasn't, this wasn't, this wasn't, this was problematic. And you could do that, you could generate that by just like having some interface that lets you highlight the problematic parts and just storing that off, right? But you'd have to get at that type of data set before you could develop something like that. And there are tools for creating data sets like that. We use some of them internally. There are open source tools, I think, is...
Prodigy? No.
No. It used to be, did it used to be open source?
No, not that I was aware of.
All right. I thought they... So there's a tool called Prodigy. I'll give a shout out to Explosion.ai. There's a company that develops an open source toolkit called Spacey, which is really, really awesome for text processing. They also have a pay tool called Prodigy, which lets you do that type of annotation. And it's a really cool tool. It does that job pretty well.
Mm-hmm. Experience with phonics or any ways of like taking, you get the model where you want here and of course it's working well, and then you want to use it in production.
Mm-hmm.
Do you just set up a last server endpoint kind of thing, and you could just call that predict method with, or do you like a good way of going? I know TensorFlow has like their whole world of TensorFlow serving stuff. So
Yeah. So If I were to deploy a torch model right now, we have a framework that will set up Flask apps for us, like software as a service that we use, that will take like a function and deploy that as a Flask app and do all the wrapping and stuff and the serving for you. So that's how I would do it. But yeah, there are a lot of frameworks, and I'm actually interested to see where PyTorch goes with stuff like that, because to your point, like TensorFlow is already like thinking about that and actively.
ONNX. The basic code actually behind really is that focus on image and the open source efforts. But there's also other frameworks which is NLP coming up that allow you to create a PyTorch model that you can actually now deploy it with PyTorch model and or we can take any particular deploy and deploy this and then start with it.
Yeah, I mean, at the end of the day, all your model is the model architecture, so like the components that you have, and then individual weights. You can even like just take weights from a model that you've developed in PyTorch and just export them to the same exact architecture in a different framework as well. So, and there's lots of like active research into doing that for different platforms, like if you train something on your computer, how do you get that onto mobile, etc. So. But yeah, we use good old Flask because Flask is cool. So back to the talk. So before we were encoding a sequence to a single vector, and now we want to encode a sequence to a sequence of vectors. And if I go back a few slides, I had a limit on this sequence to sequence discussion that I started, where the input sequence is the same length as the output sequence. So you can, if you just use a single LSTM, that's a constraint that you have. Now, you could model it if you're like chopping words out, doing extractive summarization. Your output sequence could be shorter than your input sequence because you're explicitly saying, I want to chop out these words. But this would be for modeling a sequence where you have an output from your model for every input of your sequence. So if we want to implement part of speech tagging, we have our good old perceptron up here. So we just send in different words, and we're probably going to use word vectors again because they're cool, and that's what the cool kids do. We send this up through our LSTM. It outputs something, and we run a perceptron classification on it. And it says this is an adverb, this is an adjective, this is an adjective. And the difference here is we no longer just have, for every batch that we send through, or every single example that we send through, we're not just going to be calculating the loss on a single example, or a single vector with respect to the target. We're going to be calculating the loss on multiple examples with respect to the target. So each one of these guys is going to be a vector of probabilities, and each one of our targets is just going to be an integer. So we're going to have, if we just pass one sentence through, we're going to be computing the loss for an example that is the length of that, a number of examples that is the length of that sentence. Mm-hmm.
So how do you actually find the eventual loss of each and every term? You take the average will be calculated less than the loss?
Oh, for those, yes. So the loss function typically has a way to, it typically has an input parameter that tells you what you want to do there. You can return all of the individual losses if you want, or you can sum them or average. Those are the typical ways to do it. I think that the default is averaging, and it's usually done instead of, so if you take this picture and kind of tip it on its side, it's really just treating all of those as a batch, like with mini batch stochastic gradient descent, you're sending batches through anyways. So Torch has really robust methods to deal with that and to take care of that. But we're just sending through single examples at a time because I don't want to deal with like 4-dimensional tensors, and it's beyond the scope of this particular talk. So any more questions before we dive into more code? Can you guys see this okay? See the code okay? Should I make it bigger? Is that good? Yeah, I don't think anything should be cut off. I try to stick to the PEP 8 standard and not have super long comments. So here we're going to pull in a data set called the Penn Tree Bank part of speech corpus. So this is actually included with NLTK, and if you go into the data acquisition notebooks that I have, you'll see where I just import NLTK and literally just pull this thing out. And what this is it's two parallel sequences. So the first one is just a list of all the words from a sentence. And the second one is just all of the part of speech tags for that. And I think that it includes multiple languages, or at the very least includes different part of speech tagging nomenclatures, if you will, so different things that they call different parts of speech. And I think that there's like 80 or 100 different variations, across the board, and I've boiled it down to just 12. So there's a way that there's like a method in NLTK that lets you just boil this down to just 12 parts of speech. So we have this input sentence, and we have noun. Any punctuation is actually separated off by, so in the tokenization, punctuation is its own token as well, and that's learned as well. So the punctuation label is just a period. So again, I'm going to figure out how many words there are and create a word to index and label to index vectors. Or I'm sorry, lookups, and then just calculate my vocab size. So a lot of this is going to look almost exactly like the previous example until we get down. So actually, all of this is going to look exactly like that. Nothing's changed here, except for the label size. Label size is different here. But what is going to change is as we're passing through this, or actually, can anybody tell me what's going to change when we do our forward pass here? I think that there's only like one line that I had to change for this from the previous example. I shouldn't tell you how little effort I put into this. So before, when we took the tensor that was the output from our LSTM, this is sequence length times hidden layer size, right? Because we have an output for every element in the sequence. And for classification, we just took the last element of that sequence. We just wanted a single vector to represent that whole sequence. So before I fed that into our linear layer, right here I had final output of -1. I just took the last element of that sequence of my LSTM output. But now, right here I had final output as LSTM output of -1. Here we're going to keep the whole that whole series of outputs because we want to classify each one of those things, each one of those vectors that was output. So I'll just run this whole cell. So I'll just walk through really quickly. So first we convert to tensors, run them through our embedding. So this produces vectors of length 100, I think. Then we're going to unsqueeze that to pop our batch size of 1 into the middle of that tensor. Then we're going to, we already initialized our first hidden state. So this is that tuple that has the hidden vector and the context vector. And we're going to pass through our embedded sequence. And we have the hidden state output, which is the last hidden state from the LSTM. And we have our LSTM output, which has a vector output for every element in our sequence. I just put this in there because this is where I took off the -1 from before. And then we are going to pass that through our linear layer, take the softmax of that guy, and this is the softmax over all of our, whatever dimension our classes are, because we want to, over all of our classes, convert that into a probability. So we don't want to take that over our sequence length, so you have to be careful what you calculate the softmax over. This gave me a bit of a headache a couple nights ago, so yeah, just be careful with, when you define your softmax. Here I specified that I want to use dim equals 2, so along the third axis. And then I calculate the loss. So you can see I start out with my feature shape, my feature sequence shape is 18, my target shape is 18, this guy is 18 by 100, which is what I expect. I have 18 words in this sequence and I have 100 length vectors. After I pass it through my LSTM, now I have a sequence still of length 18, and I have vectors of length 50. So those are my output vectors, and now I want to use those to classify each one of those things. So I have 12 different output classes. So after I've run it through my linear layer, this is just a matrix transformation with whatever weights are stored in that linear layer, still give me an output of length 18. My sequence length is still 18, but my output vector is now the right dimensionality, the same dimensionality as my number of classes. Then I run my softmax on that, which should not do anything to the shape, right? Because it's just a transformation to normalize. And then I actually squeeze that guy, so I take out that middle dimension here. So unsqueeze inserts a dimension, squeeze takes that dimension out. And I do that because the loss function is only expecting this dimension. So I'm essentially treating this guy as my batch size, like I said before. And then that's my loss. So now this part of speech tagger looks almost identical to the same model that I showed you guys a few minutes ago, so I won't open up Sublime again. And then we can let this train for a minute. So while this is training, I actually want to let this train for, I think, 5 epochs. So do you guys have any questions on part of speech tagging or sequence-to-sequence models where the sequences are the same length? No? You guys stoked about PyTorch now?
What's the best resource you think? We're just coming back to this next week or the week after.
So I would, not to toot my own horn, but I would recommend these notebooks because they're like all the spots that I haven't filled out are like the necessary steps that you're going to have to walk through in any tutorial anyways. Yeah. And then the PyTorch website has awesome material. They have really, really good examples.
When and how do you choose your sequence length? Because if you don't line into a document, normally you sample segmentation, that could be from 1 to 20 or 100 words.
Yeah. So
do you change like dynamically percentages, or do you?
So the sequence length is just whatever the sequence length is for that particular input that you're feeding in. So that's the cool thing. You're feeding in this variable length thing, and you're creating a fixed length representation of that. So for
the document,
yeah. So if you run an LSTM on the entire text of a document, you're also going to have a bad time. You don't want to. It's going to. LSTMs are notorious for being slow to train. So there are other ways to like you can run a convolutional neural net over the word vectors, and that would be something that's slightly faster. You can also, there's something that's relatively new called an intention mechanism, which you can use in lieu of using an LSTM with just the word vectors as well. Those tend to train a little bit faster. Or you can just chunk up your document. So we've done things where we just take our whole, even like a paragraph in some cases is too long, right? So you just chunk that, either you use a sententizer to just chunk that into sentences and then each sentence is your input, or you could just like randomly chunk, like take random subsequences of that paragraph to train. But you don't want to have your sequence length be over, I don't know, maybe like 30 or 40. I don't know, if you have a GPU or like a GPU cluster or something that you really want to like make the fans run on really hot, then you can run a ton of data through it.
You said the maximum is when you could process sequentially each of your sentences.
Yeah. I wouldn't do too much more than, I don't know, like sentences or like a short-ish paragraph through an LSTM. I tried the middle of last year and I had a bad time, so I would not recommend it. Let's see. Yeah, so this guy is learning. I'll let it finish. I think there's 5 epochs here. No, I have 10. I'll let that guy keep running while I run through the last section. So before I start this, it looks like we're going to run out of time, so I'm happy to stay around and finish this section, or I'll just try to run through it relatively quickly. But now we're going to talk about, might have to zoom out here a little bit. Now we're going to talk about actual sequence-to-sequence modeling. So if you talk to a deep learning practitioner, they wouldn't call what I just described to you sequence-to-sequence modeling because it had the limitation that the input sequence was the same length as the output sequence in terms of your actual targets. So your target length had to be the same length as your input length. So a true sequence-to-sequence model doesn't have that constraint. So it uses something called an encoder-decoder architecture, and this is really useful in things like neural machine translation. And a model not terribly more crazy than the model that I'm going to show you was, I think, the first iteration of Google's Google Translate engine. So it's not like these things work really well if you throw a ton of data at them. This is the only example where it's not going, I'm not going to let this thing train and show you guys any results or anything because they take a long time to train with a ton of data. So like on the order of like weeks with large GPU machines and huge corpora of data. So if we have variable length sequence to sequence, so the length of our input is not equal to the length of our output, we can't just use the outputs from our LSTM because we don't know what the length of the output should actually be. We can't add outputs to that thing. So we have to figure out another approach. And the easiest thing to do is just come up with some sort of an encoder that encodes a sequence, and then have a decoder that takes the encoding of that sequence and decodes it into another sequence. So LSTMs are good for sequences or recurrent neural nets in general, so we could probably use a couple of those. So the basic architecture looks something like this. We have our encoder here, the quick brown something fence. And we have the output in Spanish here, and we just have an encoder that encodes it into a fixed length representation that we hope captures all of the information from this input sequence, and then we feed that context into our decoder, and that produces a sentence. So this seems like pretty cool if we could get this to work. There's a lot of really minor details that make this a little bit challenging to implement. They're not really hard, but it's just stuff that you wouldn't really think of. For example, how do you know when your output sequence is done? Like, how do you know when you're at the end of the sequence? Because this thing, if it's generating text, if it's just figuring out what the next word should be, it could just go and do that forever. So the underlying architecture for that is just 2 LSTMs. So you have your encoder LSTM, and all you do is pass through your input sequence through the entire LSTM and then just grab grab the output state like we were doing for our simple classification model. So you just grab your final, this final output from here, or actually we're going to grab the hidden state from down here. So that should encode the same thing, except it has the cell state with it as well. And then we are going to initialize a second LSTM, our decoder LSTM, with this context vector. So up until now, I've been initializing the hidden state and the cell state for all of our LSTMs with just zeros. So I've just been saying, I don't know anything about what this should be, so I'm just going to initialize that with 0. Here we're saying, I'm going to initialize it with all the information that I had from my encoder. All the information, the fixed length representation that I had from my input sequence, I'm going to feed that in and seed my output sequence generator with that. And then again, we just have our perceptron classifiers up here, except up here, instead of classifying just like a small number of classes, this is actually going to be a really, really high dimensional perceptron classifier. This is going to have one output dimension for every word that's in your output corpus. So if you're translating from English to Spanish, this is going to be a very, very long vector of Spanish words that's going to contain a probability for being each one of these words in your second language. So sorry to context switch, but this guy finished, and I just wanted to show one kind of cool feature of this. It's not working now. Never mind.
Words are right.
Yeah. So this is working. So when I trained this before, so when I first saw this is just running a sample sentence through. I went for a run today. So here, run should be a noun, right? When I fed it, there's a little bit of ambiguity here, but when I ran this sentence through before, run was a verb. So it shows that it's not just it's not just learning a one-to-one mapping. It's actually learning contextual clues. This isn't proving my point, but I promise you it did earlier today. So yeah, but it is at least learning some sort of part of speech tagging here. So back to our encoder-decoder architecture. So we have an encoder, which is an LSTM, grab the final hidden state, feed it in, initialize our decoder LSTM with that hidden state, and then have a very high-dimensional perceptron classifier for each one of our output states here. For our input, this is where I was saying that it gets a little bit weird with things that you wouldn't think of. We actually have to introduce some new tokens into our language. So specifically a start of sequence and an end of sequence token. So the end of sequence is going to be used down here when we know that we want to tell us that we want to truncate our sentence, that we got to the end of our sentence. The start of sequence is going to be used to seed our sentence, to say we want to start a sentence for our decoder. For here, it's not as important, but it's just as easy to slap those on anyways. It doesn't hurt anything. So these are just like new words in your vocabulary. So you have start of sequence, and then you just make sure that you seed your output LSTM, your decoder LSTM, with a start of sequence, so it knows that this is starting. When we're calculating the loss, we want to take the prediction from each one of these guys, but we want to, so the sequence that we feed in down here starts with start of sequence and goes to the end of the sentence, but it doesn't have the end of sequence. So we take the start of sequence, but we don't put the end of sequence on there because we want it to produce the end of sequence. We don't want it to learn to produce an end of sequence from an end of sequence. That creates this kind of loop in the training and messes things up. So you want to feed in an input that's shifted one over from the output that you're trying to predict. So we start it with a start of sequence. We want it to predict the first word. Then we feed in the first word. We want it to predict the second word, etc. And then we feed in the last word, and we want it to learn that at the last word it needs to produce an end of sequence. And then when we run inference on the model, when we're just feeding in words, we start it with a start of sequence. And then as soon as it gets, this thing can generate words all day, as soon as it gets to an end of sequence for the first time, then we cut it off, and we say that's the translation. Any questions on that? Yep, sorry.
So you can set up your encoder to have whatever size output you want. Why do you take the hidden state and not an output vector?
So actually, the hidden state and the output are actually the same thing. So the cell state is something different, and I'm saying that I'm pulling out the hidden state here just because I'm feeding into a new LSTM, and I just want something to occupy the cell state as well, and I didn't find anything good in the literature. But in the literature, they say that they usually just pull out the hidden state. But yeah, the hidden state, if you go back to that LSTM diagram that I have, the arrows at the top that go to the output and to the hidden state are actually, it's just splitting off from one arrow. So it's just, they're the same thing.
So I have a second question too. Are you feeding in dense representations or one-hots to this?
Dense.
And I guess the real question is, why are you then outputting to one-hots? Is it okay to output to a dense representation and then do something like a nearest neighbor lookup or something to find what?
Yeah, that's a good point. I haven't seen anything in the literature with doing that, but I think Matt works with me at S&P, and he has his hand up.
Well, ultimately what's happening here is you've got a giant table of dense embeddings for your vocab in the output language.
Right.
And you're just dotting, you have an output hidden state that's the same dimensionality as those vectors, and you're just dotting that with each of the words in there. And then you're softmaxing that. So essentially you are kind of doing a cadence, because where they overlap the most, you'll get a big number in that output. So it's kind of, I mean, you can think of it sort of like a nearest neighbor sort of lookup. Like that wherever the softmax activates the most, that's the most similar vector to the output sort of, if you look at the map.
Can you say a little bit more about that context and in terms of what it is and what kind of representation it is, and especially how it relates to the length of the input sequence? Because presumably that context has to have information about the full input sequence so it can do a translation.
Yeah. So the crux of this type of architecture is that you hope that this fixed length context vector, it's a fixed length vector. It's just whatever the shape of your hidden state was, is able to encode all the information that was contained in your input sequence. So if we go back to sequential models, this is essentially the context vector right here. We're just taking the last output or the last hidden state and just feeding that in as our context vector. So we're just looking to come up with some sort of representation, and that has by how the architecture is put together, that should have information about every part of the sequence. I mentioned bidirectional LSTMs. That's typically what people will do. Like if you look at people that have more than a 15-inch MacBook Pro and they can run more stuff, they'll have like a multi-layer LSTM that's bidirectional. So then you're capturing information going both directions using multiple layers. So you're using, and then that each one of those layers will have an output vector, and then you can just concatenate all of those. So then you have, instead of just like a 50-dimensional vector from one LSTM, you have 150-dimensional vector from 3 LSTMs, and then they're all capturing different levels of information about your context. So that's like if you go to most of the blogs out there that are talking about this, or research papers, that's typically what they'll do. And then there's more advanced techniques that allow you. So by doing it like this, we're just throwing away all of this information that we have here. Like these things are useful. There's no doubt about the usefulness of these. And there's other approaches called attention mechanisms that allow the model to learn how much it should pay attention and include information from each one of these output states as well. So you basically get like a softmax distribution over each one of the words in the input sequence. And those are really cool models too.
What's a typical dimension for that?
What's a typical dimension for what? The hidden state? Oh, the context? It depends on, if I'm training it, my typical dimension is like 100 to 300. If you look at like Google, this will be like 1096 or like 2000 or something. So they'll use really, and I mean you need to do that when you're training with a ton of data. Like they'll train on like all of the data that Google has accessible to them for a month at a time, and to like really produce a good version of their Google Translate product. So. You want that to be able to contain a lot of tunable parameters because you're throwing a ton of data at it.
Are there some attention mechanisms implemented in PyTorch itself, or do you pull in other repositories that have implemented?
Oh no, actually it was hard for me to find any examples of this. So everything now, even the default example on the PyTorch tutorials website says, oh yeah, there's this encoder decoder thing, but here's attention. So they're like, that's kind of like the standard now. Okay. This is just like a pretty basic version that does the trick as well. Cool. Any more questions? All right. So the last thing that I want to talk about with this is teacher forcing. So this example here, where I'm talking about training it and calculating the loss, this is with 100% teacher forcing. And what I mean by teacher forcing is I'm feeding in the known output sequence as the input, regardless of what the last output was. So in practice, I don't know what that output sequence is, right? But when I'm training it, I do. So teacher forcing says, well, I'm going to teach the model what the right next output should be by just telling it, feeding that in as my input for the right next output. But most implementations of this have what they call a teacher forcing ratio. So some of the time you're going to do this teacher forcing, you're going to feed in the known label. But other times you're actually going to just take the predicted value for the next thing and feed that in as your next input. And this helps to, from what I've read, this helps to prevent your model from learning sequences of words that fit together, but don't necessarily make a ton of sense in the context of your of whatever your problem is. So you might get a word that like kind of makes sense, like you can see how these words fit together. Maybe you can sneak it by like your dissertation advisor or something for like half of your PhD thesis, but not the whole thing. So cool. So for inference, like I was saying before, you would take in your input sequence, convert it to a context vector, and then you have no idea what the expected output is, right? That's the thing that you're trying to figure out. So all you can do is just seed this with a start of sentence vector, and then you take the prediction for the previous one and keep going until you hit an end of sequence, and then you just cut it off, and then that's what you return as your actual value.
And there's no guarantee that you'll ever hit the end of sequence.
No. So you usually, in most implementations of this, you'll see some sort of max cutoff, and I actually have that in this notebook.
So I've seen other applications other than language translation for sequence predictions, and I've seen them use as inputs to each of the time steps for the decoder, just repeated context, like the context we have there. Like,
Yeah.
Is there any, like, in general, like, is one better than the other?
I can't speak to whether or not one's better than the other, but I have seen that as well. So a lot of times what I'll see, they don't just input the context vector, but they concatenate the context vector with the actual input, or they'll stack them on top of each other. And if you think, this is why I like neural nets so much, because you can kind of think of what that would do, right? Instead of just saying, I want the information from the encoded sequence to just be input in the beginning, you can say, well, I want that to be carried. I want to ensure that I carry that along for the whole length of my actual output sequence generation. So you're just enforcing that instead of like the encoded information is going to be there for the whole time that it's decoding. Cool. Any more questions? So we are 10 minutes over, and I have the same exact walkthrough. Oops, I want to do that. We have the same exact walkthrough for the other one, but I'm just gonna breeze through it so I don't keep y'all too much longer. So have all of my imports here. I do the same exact thing that I did for the other ones, cleaning up the text a bit, and then I'm just gonna slap on the start of sequence and end of sequence token. And I'm going to do that before I calculate my input and output lookups. So I calculate those guys. And then here I just create input sequences and output sequences. So input seeks. So that's just it's just a whole bunch of lists of vectors, or of integers, sorry. So if we want to create all the individual components for this, we need an encoding embedding layer. And I'll set the embedding dimension equal to 100. And then we need an encoder RNN. That's all that we need for the encoder, because we don't need a softmax, we don't need any of that stuff. We don't need a linear layer because we're not doing anything with that. We just want to feed in the raw output of this. And then for our decoder, we need a decoder embedding layer and a decoder RNN. And the decoder input size, the decoder hidden size has to match whatever you're feeding in from the encoder to the decoder. So the context vector, this has to be the same as this if you're feeding in the hidden state. If you're going to concatenate things, like if you have like a multi-layer RNN, then this should be, like if you had a 2-layer RNN, then this would be 100 if you were just going to concatenate those things on top of each other. And then for our decoder, because we're going to be doing actual classification here, we have a linear layer that's the output, the hidden layer shape, the hidden dimension of the decoder LSTM, and then the output size. And then we apply a softmax to that, and then we have a log softmax to that, and our negative log likelihood loss. So define all of those guys, and then we can just pass this through, and then this I think will be the last step, so I'll just talk through this. So our input sequence tensor shape is just a sequence of 16 integers. Our output sequence shape is 13, so this is, we don't have equal sizes for our sequences. And we run our input sequence through our embedding, and then we get a sequence of 16 100-dimensional vectors. Then we pass our... then I squeeze that guy. Why do I have this here? I think that I don't have the shape right there. Yeah, so our encoder output shape is going to be 16 by 1 by 50. So this is our batch dimension. This is our sequence length, and now we have an output for each one of those. Our hidden shapes for our hidden vector, our hidden state is going to be 1 by 1 by 50. And our cell state is going to be 1 by 1 by 50. So we're going to pass in this tuple of things into our decoder hidden state to initialize it. Our decoder embedding, again, 13 by 100, 13 by 100. We're going to pass that through, and our LSTM input shape is going to be 12 by 100 because we want to strip off, when we're feeding in doing teacher forcing, we want to strip off the end character because we want it to predict that end of sequence character. So we're going to start with the start of sequence, but strip off the end of sequence. And then for our output for that, this is our linear output shape, and then our output target shape is going to be 12 as well because we're stripping off that start of sequence. We want to match up the start of sequence with the word after the start of sequence. And then this is just verifying that the softmax is actually doing a softmax as a check. So if I sum over all of the 15,000 dimensional representation of all of the 15,000 words that I could have after I run a softmax on that, I expect that to sum to 1, and I expect there to be 12 of those because I have 12 elements in my sequence. So this is just a sanity check to make sure that things are working. And then this is everything encoded as a PyTorch model. So the only other thing that I'll mention here is, notice I have an encoder module, I have a decoder module, and then I have a sequence-to-sequence model where I initialize that sequence-to-sequence model with an already created encoder and an already created decoder. And this initialization could even create those things if I passed in all the input parameters that I wanted to for that. And then I have a forward for this guy that just calls, it walks through and initializes the hidden states, passes the encoder, or passes the input sequence through the encoder, grabs the hidden state of that, and calls it the decoder hidden state. and then loops through the individual elements of the decoder, the output sequence, and based on some sort of a probability of teacher forcing, it says, do I feed in the inputs or the actual output sequence, or do I feed in the output from the decoder for the next one? And then I just return the stacked output of that guy. So that gives you all of your individual integers. And yeah, this guy learns really poorly on this small data set, but I can let it run for a second. That defines all of them. This will train it. So notice how I'm just creating a sequence-to-sequence model, and I'm only calling .forward on that. So it's really cool how you can just, how PyTorch models can just chain on top of each other. So you can just create a module and then use that just like I've been using linear layers as a component of another model. So I stopped that really quickly, and then this is just the predict method, so it actually predicted a sentence, but this didn't end in an end of sentence. So it would have just gone on for a while, so I stopped it. So yeah, we are officially well over time. So thank you everybody for your time and paying attention.